Now we will listen Kyrylo. Thanks. You can go.
Thank you very much. Thanks a lot for inviting me, for giving me the opportunity to present this work, and for organizing this beautiful program. The program is called Quantum Trajectories, and I'm going to tell you a story of quantum trajectories, but not of usual quantum trajectories, not the random ones you get from measurements because you don't know the measurement outcome. Instead, I'll tell you a story of quantum trajectories which you create by hand in order to improve the calculation on a quantum computer. And before I go into details of that, let me say a couple of words about trajectories in Ukrainian embroidery. Here I'm standing in a kurta, which is an Indian traditional dress. We have something similar in Ukraine called vyshivanka. This is an embroidered shirt with this embroidery, which can come in different colors, but often it comes in two, red and black. There is even a song about that. And the red stands for love in that song, and the black stands for sorrow, which tells you the life does not always go the way you want it to. And that's definitely the case for quantum computing. This is a recently published paper where we tried to simulate the dynamics of the BCS model on a quantum computer. We started with some initial state, simulated the dynamics, and ideally the result should have been the black curve. On a perfect quantum computer with our method, you should have gotten the red curve. And in reality, on this older IBM machine, we got this, which is frankly speaking horrible. And then we also tried a newer IBM machine. Now there are much newer and significantly better machines. Still, the results here were not perfect, and on the best today's machines, they wouldn't be perfect. And the reason for that imperfection is noise. Basically, your circuit involves some 2-qubit gates, and there is some noise, so every time you apply a 2-qubit gate, there is some error in your calculation, and this error does not allow you to achieve perfect results. Let's look in detail how exactly these errors work. What we did, we tried to simulate dynamics of this BCS model, so the superconductivity model, with 3 qubits, 3 Cooper pairs. Not impressive, I know, but was sufficient for our purposes of testing the machine. On a gate-based machine, you cannot really implement this Hamiltonian evolution. So what you have to do is to break down this unitary evolution into small time steps, into Trotter time steps. Then you can take different terms of the Hamiltonian apart, and these are implementable by some combinations of gates. So here you have a sample circuit, some state preparation, and then single qubit parts of the Hamiltonian, 2-qubit interaction, another, yet another. You have some 2-qubit gates because you need to implement interaction. You have some 2-qubit gates because the interactions are all-to-all and the connectivity on the machine is limited, so you need to swap qubits. The result is 9 CNOT gates per Trotter step. And CNOT gates, even on those older machines, they're reasonably good. They have something like 99% fidelities. But 99% fidelity means a 1% error probability per CNOT, which means 9% error probability per Trotter step. So after about 11 Trotter steps, you expect to obtain complete noise. Yet we were able to recover the results. We did something called error mitigation, and we were able to get reasonably decent curves out of the quantum computation. You see, they are not perfect, they do not perfectly coincide with the red, but this green curve is not too far, definitely much better than this yellow. And also notice that this is Trotter step number 15. You expect complete noise after about 11, but it looks like complete noise significantly earlier. So how did we manage to recover the results out of the quantum computer? That used 2 error mitigation techniques. The first one is called noise estimation circuit. Let me give you an example how it works. Imagine your quantum computer has global depolarizing noise. What does it mean? Every time you apply a C-naught, all the qubits experience depolarization, so with some probability you replace the density matrix of your quantum computer with a completely mixed state. If your noise is like this, which is drastic but also simple to treat theoretically, then any expectation value you will measure at the end will be simply suppressed by this damping factor. So if you know some observable to which you have the exact answer and you measure the answer from the quantum computer, you can learn this damping factor and cancel it. The problem is, how do you know the outcome for some observable of this complicated circuit? The answer comes from this beautiful paper, which says the noise typically comes from 2 qubit gates. So let's ignore the single qubit gates. What remains is rather simple. These 2 C-naughts cancel each other, these as well, these as well. This just implements a swap, so I can track the result, I can predict the result of this circuit rather easily. And at the same time, it has the same noise characteristics as my original circuit. So I can call it the noise estimation circuit and define my mitigated expectation value by the measured expectation value with the full circuit divided by the fidelity, by the accuracy of this noise estimation circuit. I kind of measure the observable, which should give me 1, I don't get 1, and this tells me the suppression factor. That's, of course, for this global depolarizing noise. The noise doesn't have to be like that, but the hope is maybe this method also helps for more realistic types of noise. That's one part of the story. The other part of the story is so-called randomized compiling. You have a C-naught, you have something happening on the quantum computer, and in principle, anything can happen. So this noise channel is extremely complicated. It should be parameterized by 240 parameters. It's very hard to think of, very hard to do something about it. Was that a question? No, okay. It's complicated. And the randomized compiling, which comes from these papers, it says, put some random Paulis around your C-naught. They're random, but they're cleverly chosen. This R and S are chosen in such a way that if it's perfect C-naught, it remains a perfect C-naught with these extra Paulis. But if it's noise, the noise direction will be changed. So you randomize the direction of noise, and averaging the results of different circuits with different random gates, you effectively get a simpler noise channel, a Pauli noise channel, where what you apply on the left and on the right of the density matrix are the same Pauli matrices, and you only need some 15 probabilities of different Pauli noises. We went a bit beyond that, and we said, we do calculation with 3 qubits, and naively you'd say the idle qubit does not experience any noise, all the errors happen here, but in reality, it's not the case. So we extended this randomized compiling to this 3rd qubit to make depolarizing noise on the idle qubit. And how do I know crosstalk is important? Well, here are the data without noise estimation circuit, so it's not mitigated, just randomized compiling. The original data are yellow, the data with randomized compiling but no crosstalk taken into account is blue. It doesn't change much. And when I do something which involves crosstalk mitigation, the data change a lot, which tells me crosstalk is actually significant on these machines. Now IBM has changed the architecture, but back in the time, crosstalk was significant. And you see, it doesn't give me the perfect red curve, but that's because I didn't use the mitigation. Now I add neck, and this is my green curve mitigated, which looks reasonably decent. Not perfect, but decent. So that's the story of that paper. Yet today I want to go beyond it. What we thought after we've published this paper is we have this assumption of global depolarizing noise for noise estimation circuits. Global, well, will not make noise global on a quantum computer, especially if you use many qubits, the noise will happen somewhere locally. But depolarizing, our noise is Pauli. Randomized compiling makes it Pauli. What would happen if we had true depolarizing noise? Perhaps we could improve the results even more. And before I tell you what happens when we make this depolarizing noise, I want to tell you how at all is it possible to modify the noise structure on a quantum computer. It's something which comes from the hardware. Can I modify the noise structure on a quantum computer without touching the hardware? I see a question. Oh, they basically had these couplings between qubits on all the time, which means you don't want these qubits to talk to each other at the moment, so they tune them off resonant. But nevertheless, there is some interaction, residual interaction. Whereas now they change the architecture to the same as Google uses, that they can detune this coupler, that the coupler also becomes switched off, and that reduces the crosstalk quite significantly. Okay, so how is it possible to modify noise without touching the hardware? Is it possible at all? Turns out it is, and this comes from these beautiful and very counterintuitive papers, but turns out to be rather simple. What this paper says is that imagine you have your Pauli noise, you can do something to your circuit and cancel it completely, or maybe reduce it. These techniques are called probabilistic error cancellation and probabilistic error reduction. And what you need to do for that is you need to add more noise to your machine. In fact, what you need to do is apply, again, some random Paulis. You choose them in a clever way, and it turns out that this applies some tailor-made noise channel, which together with the hardware channel gives you the noise you want, which might be no noise whatsoever, which is extremely counterintuitive. How can it be I apply more noise, more randomness, and I cancel the noise completely? That's very strange. In order to explain you how it works, I need to introduce two representations of noise. One is the chi matrix representation. I have my density matrix, the noise acts, there is some Pauli acting on the left and on the right of the density matrix, and the contribution of these terms is parameterized by the matrix element of this chi matrix. If I have my Pauli noise, it's diagonal. The Pauli on the left and on the right are the same, so the matrix is diagonal. I can introduce the probabilities add up to 1. Well, they're proper probabilities. The second representation I will need is the so-called Pauli transfer matrix representation. I can say the density matrix can be decomposed into the Pauli basis, and what the noise does, it's a linear map which changes these coefficients of the decomposition. So this EAB is the Pauli transfer matrix, the transfer matrix from initial to final density matrix in the Pauli representation. And for the Pauli noise, it happens to be diagonal as well. The two representations are connected by the Walsh-Hadamard transformation, which is a linear transformation which takes into account that some Paulis commute with each other and some Paulis anti-commute with each other. So two transformations. It's very simple to think about noise in terms of the chi matrix. Imagining Pauli transfer matrix is much harder, but it has its advantages because now I can compose different noise channels in terms of matrices. I say there is this gate noise on my machine and there is this tailor-made noise and I wanted to make a target channel. Well, I need to multiply the two matrices to get the target channel. And I can invert the matrix multiplication, say, so the tailor-made noise channel should be the product of this. I get these diagonal elements. I employ the Walsh-Hadamard transform, get the probabilities. And so I know with what probabilities I need to sample my Pauli matrices to do what I want to get the target noise channel. Sounds very impressive and counterintuitive. We've just created some trajectories by hand. We run some random circuits, average them, and in the average, it looks like the target noise channel. So this is what these papers tell us. Sounds too simple. There must be a catch somewhere. Indeed, there is a catch. If you do this procedure and you want to reduce your noise, these probabilities come out negative out of the transformation. What is negative probability? Yeah, that's a problem. So let me rename them into Qs, quasi-probabilities. How do you sample a quasi-probability distribution? What you can do is you can define the absolute values of these Qs and sample them as probabilities. And then when you do the average, well, you know which of the Pauli applications should have come with a negative sign. So you take the sign into account by hand when you calculate the Monte Carlo average. There is one more subtlety. The sum of Qs was 1, but I took the absolute value, and now the sum is above 1, which means to make it a proper probability distribution as a sample, I need to downscale it. And then correspondingly, to get my result back, I need to upscale the average at the end by this factor gamma. For every C naught, I need to multiply it by gamma, so gamma to power C naughts. And that is a problem, because if I want to keep a fixed error bar on my observable, you know, there is some shot noise, there is some sampling noise. And if I multiply the result by this exponentially large factor, my error bars also scale, they become exponentially large. So I need to increase my sampling exponentially. This is the curse of all error mitigation techniques. They're actually costly. The true advantage of quantum computation can only come with error correction, not error mitigation. But for now, we are playing with this. On the light side, that's not very different. That's not something that's completely unknown. This is very much like the sign problem in the usual Monte Carlo. When you Monte Carlo sample a function which can be negative, you get this exponential cost to get the result accurately because different terms are supposed to cancel. Nevertheless, this PEC and PER are techniques with which people played a lot. And sometimes you can even get around this exponentially costly thing because this factor only comes when you try to reduce noise. And if you try to increase the noise, well, there are no quasi-probabilities and no exponential factors. And this is what IBM used in their famous quantum utility paper. They simulated this Floquet-Ising model. They did tomography of their computer. They knew the noise. And they used this technique to increase the noise a bit and a bit more, and then extrapolate the result back to what it would have been if there was no noise on the quantum computer. And they got reasonably good results. Although they didn't quite help them to establish any sort of quantum advantage, because a few weeks later, their results were reproduced on a classical computer, and less than a year later, they were reproduced on an ancient classical computer. Nevertheless, people use these techniques, they investigate, they try doing things and seeing what comes out. So that was our idea. Let's try to make our Pauli noise depolarizing. So we have our Pauli noise channel. We could have tried to remove it. We could have tried to reduce it. But let's just change the noise structure to suit better our favorite error mitigation technique, the noise estimation circuit, and hope that the cost, this exponential cost, will not grow as fast as with PER and PEC. So this is the protocol of what we've done, and what I'm telling you has not been published. Hopefully it will be on the archive in a couple of months. So the protocol is like this. We need to do randomized compiling to turn the complicated hardware noise into more tractable Pauli. Then we need to learn it. We need to do Pauli noise tomography. We need to decide what is exactly the noise channel we're aiming for. Then we calculate the quasi-probability distribution. We sample it, which effectively gives us the noise we want, and we get the results for the expectation values of observables and see how good they are. That's the protocol. Does it work well? Should it work well? Let me start with the classical simulations. I'm saying classical simulations, but in fact they are classical simulations with the Pauli noise we extracted from the actual quantum computer. So in reality, we applied it on the quantum computer, and for the same noise we extracted, we did some classical simulations. And this is what the simulations show. The red is the would-be perfect result. The yellow is what would come out without noise tailoring. The light green is what should come out with infinite quasi-probability distribution sampling if our noise tailoring is applied perfectly. And for finite sampling, which is what we do on the quantum machine, this is the dark green curve. So what we see is that the results, they weren't too bad to start with, and with noise tailoring, they can be improved. They still will not be perfect because the noise is not perfectly aligned with the NEC assumptions, but it is possible to improve the results. That's what the classical simulations tell us. Not bad. Now, how do we choose the target noise channel? We say we target depolarizing noise, but depolarizing noise has this parameter. And we need to choose this parameter. The noise estimation circuit is the reason why we choose depolarizing, and it divides the observable by this NEC fidelity. And then when we apply noise tailoring, we need to multiply by this exponential factor. So we get ideally the mitigated value of the observable, but if there are any errors, like sampling errors or other unaccounted errors on a quantum computer, they will be amplified by this factor. So it is reasonable to choose lambda d in order to minimize this factor, so to get as good results as possible with the reasonable sampling. So on this plot, what I'm showing is we did the simulation for many different observables, you know, X on the first qubit, Y on the second qubit, and so on. And we averaged the results. This is what we would get in classical simulations without noise tailoring. This is what we get if we choose this lambda d cleverly. This is what we would get if we just choose the average over all channels. If we say we don't try to minimize this, there are some Pauli channels, we take the average of all probabilities, that is our target. And you see, even changing the structure of noise without reducing it on average, it can bring benefits, although if you're more clever, you can do better. So that was the classical simulations. Now what happens on the actual quantum computer? On the actual quantum computer, if you look here, things go much, much worse. See, this is what the classical simulation predicted for the absence of noise tailoring. This is for the presence of noise tailoring with 10,000 samples. And this is what we get under the same conditions out of the quantum computer, which is huge. Upon some thinking, we've managed to attribute this extra error to a few sources. So this is the level you would get from classical simulations. This is what you expect. And then this part, it comes from undersampling of randomized compiling. You use a finite number of trajectories, so you do not convert the noise to Pauli perfectly. There is some residual coherent noise. That's one contribution to this big error bar. The other is the noise, the errors we discarded from our model. We did not try to mitigate in the first place. We discarded single qubit errors as being much smaller than CNOTs. But we have many single qubit gates, and eventually the errors accumulate. And also there can be non-Markovian errors. The noise can be correlated in time, or there can be leakage to higher excited states of the qubit. These are the two distinct classes of errors we've identified. Still, the question is, why are they so huge? And the reason is that they're amplified by this factor. If you de-amplify and say, what were these errors if we had not applied the NT, well, they would be rather small. But this huge factor, it amplified the errors and made the result of practical application of NT not really favorable. Now, we also did some modeling. What would happen on the real quantum machine if we did not 10,000 trajectories to sample that quasi-probability distribution of noise tailoring, but infinitely many. We had perfect sampling, then we kill these coherent errors completely, and we would get some improvement, although not as big as the classical simulations for perfect Pauli noise predict, because, well, there are other kinds of errors. How do we estimate what would happen for infinite sampling if we cannot run it? Well, we've done 10,000 samples, then we can use the technique of bootstrapping. We can say, okay, let's split those 10,000 samples into small batches. So this is what we would get with smaller batches. This is the error levels, and then we can extrapolate it to infinite sampling, and this is what we expect in the infinite sampling. So this is an extrapolation, yet a clever extrapolation, so we tend to trust it. And the layout of possibilities looks like this then. What we've managed to apply does not really bring improvement over not knowing about noise tailoring. But if it was perfect Pauli noise, even with finite sampling, we would get an improvement. And with infinite sampling, we would improve the result by about an order of magnitude. And if we increase sampling on a real machine, we would still get some improvement, although the question is the cost really worth the improvement? And for the cost, this is the diagram of execution times. As you can see, this calculation takes hours for every data point. But if you notice, a huge chunk of this calculation is dominated by classical processing. Basically, we need to learn the noise as we start using the quantum computer. Then we calculate the quasi-probabilities, and then we need to modify the circuits we sample while being online. So this is a purely classical task which needs to be done online, and it's extremely slow, but it's extremely slow because of the way how the circuit is stored, because it was not previewed that you randomly alter gates to match some distribution. So I hope, I suspect that with an improved way of storing the circuits, it should be possible to reduce this part significantly and therefore make the calculation faster, also making it easier to sample more and things like that. And in general, you want to be faster because the noise on a quantum computer, it changes, it drifts on the scale of hours. So if your calculation lasts hours, you need to redo this Pauli noise tomography from time to time. If you are faster, it should be better. So that's basically what I wanted to tell you about our exercises with noise tailoring. Before I conclude, I want to come back to the topic of Ukraine and tell you something about trajectories in lives of Ukrainians. This is a friend of mine, Alexandra, Sasha. She is a founder of the organization Medicine for Ukraine, or in short, Me for You. And she has a very unusual life trajectory. Back in 2018, she obtained a bachelor's in math. And then she spent the next 2 years playing violin at an orchestra to make her living, and at the same time preparing for a master's in biology, because ultimately she wanted to study biology, but she decided to do math first to get a proper mathematical education. She studied for 1 year, failed the entrance exam, repeated with more determination, studied for another year, and eventually succeeded and started the master's in biology, which was scheduled to finish in 2023. But in 2022, the full-scale invasion by Russia came, and she decided to interrupt her studies and started this group to provide Ukrainian military with advanced medical supplies, like more advanced medical supplies than the standard ones, which helps save lives. But why I'm telling you this is that this trajectory is not completely environment determined. It's not all about environment influences. It's not all about measurements. It's also about being handmade, about decisions. Like this decision to study math before doing biology, it's a conscious decision. It's not an environment influence. It's not a measurement. Failing an exam is, of course, an environmental influence. So as the full-scale invasion by Russia into Ukraine. But then the decision to interrupt studies and to focus on what she considered the most important thing was a conscious decision. So what I'm getting at is handmade trajectories can improve the world around us. Which naturally brings me to my conclusions. I told you about the technique of noise tailoring, so generating artificial quantum trajectories, and how it can help mitigate the noise on quantum computers. The cost of using this technique is rather high, but it's dominated by classical processing, so maybe some classical coding improvements can reduce the cost significantly. Finally, even if it does not bring the expected improvement of the results, this technique is very useful for analyzing what happens on the quantum computer, because we've been able to identify different errors of noise. So we're trying to do something practical, to perform some quantum simulation. And what we learn is, okay, our quantum computer has some coherent errors and has some single qubit and non-Markovian errors. So we can use it to characterize the noise on quantum computer, and eventually this could help improving the machines. And that's one of the ideas of this French benchmarking project, to benchmark quantum computers by application-oriented algorithms. With this, I'd like to stop, and I thank you for your attention.
How would results will look if you implement the same protocol in the current existing IBM hardware?
Can you repeat, please?
How would this result will look?
What look?
How would results on the hardware will look when you implement this in current existing IBM hardware?
In current existing IBM machines. We have not tried. As you see, it takes a lot of time and effort to implement this. So we have not tried it with the new machines. The new machines have two distinct features. They have this switch off on the coupler, so there should be much less crosstalk. And they have errors which are reduced by up to 1 order of magnitude. But in fact, it's 1 order of magnitude better on the best qubit. On average, it's maybe a factor of 2 or 3. So I would expect the results on the current IBM machines or current Google machines to be somewhat better, but not really drastically better. In this respect, their advances in quantum error correction is because they are around the threshold, and a relatively small improvement by a factor of 2 can bring you under the threshold, and that's how they're able to start seeing, going beyond break even for quantum error correction. But for actual results, this improvement, it's important, but it's evolutionary rather than revolutionary at the moment.
I'm also seeing this, since you have this very long time calculations, right? Mm-hmm. Is there any way to bypass by using neural networks?
Bypass?
I mean, is there any way to calculate the same thing using neural network? Which can
networks.
Which can save a lot of time, I guess, what I understand.
Well, I don't know. The problem, the thing that dominates this cost here, it's not actually the calculating the quasi-probability distribution, it's just some super simple matrix multiplication. The thing that dominates the cost is you go around the circuits and say, oh, there is a C0, so I need to insert 2 Paulis here. Then you go, oh, the next C0, I need to insert 2 Paulis here. And the circuits are stored more or less like strings. So you do a lot of text analysis, which is super inefficient. But since we were focused on the classical part of the stuff, on the quantum part of the stuff, we didn't pay enough attention to that when doing things. So just if we redo it with more thought, with structuring how we create the circuits, and then we just pass random parameters, we generate the Paulis, hopefully that can improve things much more. Neural networks, well, I think things can be improved in a much simpler way.
Yeah, thank you. Thank you very much.
Can you hear me? Oh, yes.
Yes.
So thanks for the talk. And I think this is more like a basic question. I'm always confused between the word, what is that? Error mitigation and an error correction. Mm-hmm. What's the difference between these two words in the field?
I see. Yeah, it can be confusing, but it's a definition you have to learn. So error correction says I can encode a qubit in many physical qubit, which will give me a logical qubit. And this encoding, it has polynomial cost. I need to use a polynomial number of physical qubits to achieve an exponential improvement in the quality of my logical qubits. So this is how people believe quantum computers will become really scalable. You can add, say, 10 qubits and improve by an order of magnitude, and add another 10 qubits and improve by another order of magnitude. So you add maybe 100 qubits and you improve by 10 orders of magnitude, and you're happy to run your calculation. That's the idea behind the quantum error correction. But for that to work, your qubit, physical qubit, needs to be good enough. It needs to have errors below some threshold. So it has just started working, There is this Google paper last year. They've managed to add 100 qubits and improve the accuracy by a factor of 2, which is impressive, but not enough to make quantum computers practical at the moment. Now, error mitigation, it says, I will not try to use these techniques which promise to be scalable, but are not within our reach. I will use just physical qubits for logical qubits, but I will try to do something clever to reduce the errors by post-processing. Like here, we ran not one circuit, but by 2 circuits, we divided one by the other, and that allows to improve the results. Error mitigation is not scalable. It has exponential cost. You have some errors, you want to reduce them, that comes exponentially costly. You saw this gamma to power n C0 exponentially growing with the circuit depth. But for the noisy intermediate scale quantum devices, that's what people try to make them as useful as possible. So error correction is supposed to be scalable in theory, but we have just started making it practical. Error mitigation is not supposed to be the way to go ultimately, but for now, that's the way to improve the results of quantum computations.
Last question. Thanks, Kyrylo.
Thank you very much.